restrained slabs, and in two-way slabs also we have restrained slabs. So the design is slightly different from what we have seen in the other case, that is in the case of simply supported case. The first thing in this case is you have to check whether it is two-way slabs or one-way slab. Once you find out that it is two-way slab, you have to check about the condition. That is, what is the condition? Are they free to rotate at the ends? Are they simply supported or not? Or is there any provision for preventing torsion? That is what you have to check. If there is the effect of torsion should be included. That is, if they are restrained against rotation, what you have to do is that you have to adopt this method. If they are restrained against rotation, means they will come under restrained two-way slabs. And in these slabs, what we should do, that is what we are going to discuss now. So the first step is that once you reach up to this point, what you have to do is that you have to split the entire slab in both the direction, that is in the x direction as well as in the y direction, into three segments, which constitute, one is your middle strip, one is called as your middle strip, and we have two edge strips. Okay, as you can see in this slide, you have one middle strip and two edge strips, and the length of these are actually given as 3/4 of your Ly. That will constitute the length of middle strip, and the edge strip will constitute Ly by 8. That is the total length by 8 on both sides. So that is how you have to split the slab in both directions, in the x direction as well as in the y direction. So if you see this figure is actually taken from your IS 456. In Annex D, you have the same figure. So they have actually kept the Ly along the x direction. So in the x direction, again for middle strip you have 3/4 Ly, and for edge strip you have a width of Ly by 8 on both sides. Similarly, in the y direction they have kept Lx, and you can see that again they have divided in the y direction also. They have three segments. One is your middle strip, and the remaining two is your edge strips, and the length remains the same. That is 3/4 Lx, and here for edge strip you have Lx by 8. 1/8 of Lx. That is how you have to split this. Okay, and you have to actually perform the design for middle strip as well as edge strip separately. And edge strip will be constituted by a minimum amount of area, that is 0.12% of the cross section. And for the middle strip, you have to actually perform the procedure which we have adopted for the previous case. So we will see how to do it. And again, there are some difference when you calculate the value of alpha x and alpha y. You have to refer some other table. So let's take up this problem and try to explain this. And again, I am repeating, you can have a lot of conditions in the case of restrained slabs. And when we go to the code, you will understand what I mean by a lot of conditions. So in this problem, we have a particular condition, a single condition. That is, in this problem, we have to design a reinforced concrete slab for a room of clear dimension. That is, it is the interior dimension of 4 meter by 5 meter. The slab is superimposed on walls of width 300 millimeters. Okay, so the width of the support is also given to you. The slab is carrying a live load of 4 kilonewton per meter square and a floor finish of 1 kilonewton per meter square. You have to use M20 concrete and Fe415 grade steel. The corner of slabs are held down. So here you have that point. The corner of the slabs are held down means they cannot freely rotate. That means they are restrained from rotating. So they come under the classification of restrained slab. And if you take the ratio of Ly by Lx in this case, that is 5/4, you can see that it is coming less than 2, or you can say that it is a two-way slab. So these are the things given in your question. So as I told you, first thing is that you have to calculate the value of Ly by Lx and classify that into two-way slab. So we understood that it is two-way slab, and from a statement given in the problem, we have understood that it is restrained slab. Now what they are doing is that, as we were doing in the previous problem, they have just assumed an overall depth of 180 millimeters and a cover of 15 and diameter of bar as 8 millimeters. All the things similar to what we have already done. Then they calculated the effective depth, and it is observed to be 161 millimeters. So based on this effective depth, as per the clause given in the code, they are now calculating the effective span, and these things we have already seen. That is why I am just rushly going through these portions. So based on the two conditions, we have to select the smaller value, and in this particular case, it is observed that it is coming as 4.161 meters. That will be your effective span, and that is in the Lx direction. Similarly, you can calculate the effective span in the case of y direction also. And the main reason why we are calculating the effective span here is that in the problem it is given as the interior dimension, inside dimension. That is, again, we know that the slab will be extended over the supports. So we are calculating the effective span. Now, after this, you have to find out the value of bending moment and shear force. And you know that in the case of two-way slab, we will be calculating the bending moment using the equation mx is equal to alpha x into w into lx square. And again, my is equal to alpha y into w into again lx square. And alpha x and alpha y were taken from a table given in Annex D. And for simply supported as well as for restrained slab, we have two different tables, that is table number 26 and 27. So we will go through that tables shortly. Anyway, so they are just now calculating the self weights, the load from the finishes and the live load. So basically, self weight of the slab, we have already assumed an overall depth of 180 millimeters. So based on that, they are calculating the self weight of the slab. Then they are assuming that the finishing load to be 1 kilonewton per meter. So the total dead load will be the sum of these two. And we have the live load, which is given in the question as 4 kilonewton per meter. And if it is not given in the question also, you have to assume some live load in this range. Then we have to calculate the factored load WU, which is equal to the factor of safety multiplied by the sum of dead load and live load. So that will come around 14.25 in this particular case. So after this, what we have to do? So now what we have to do is that we have already calculated the value of Ly by Lx, and from table number 26 of IS 456, we have to find out the value of alpha x and alpha y. Table number 26 will come in Annex D. So let's go to the code now. Next D. So in this, the first thing was actually restrained slab. Anyway, we have discussed about simply supported slab first in the previous lecture. So anyway, we will come back to this, and we have to actually refer table number 26 for getting the value of alpha x and alpha y. So before moving on to this table, let us fastly go through the different conditions given in your code. So let's see that. For restrained slabs, when the corner of the slabs are prevented from lifting, the slabs may be designed as specified in D1.1 to D1.11. So we will start from D1.1. So the maximum bending moment per unit width in the slabs are given by the following equation. Again, the same equation, that is mx is equal to alpha x into w into lx square, and my is equal to alpha y into w into lx square. And you know what do you mean by these variables? Now, moving on to the next clause, we have slabs are considered as divided into in each direction into middle strips and edge strips as shown in figure 25. The middle strip being 3/4 of the width and edge strip being 1/8 of the width. So it is given in your figure 25, which is this figure. This thing I have already shown you. So based on the dimensions, we have to actually classify it into middle strip as well as edge strip in both the directions. And middle strip will have a width of 3/4 of total length that is Ly in this direction, and we will have edge strips having a width of 1/8 of this length on both sides. Similarly, in the other direction also we will have middle strips and edge strips. That is what is given in D1.2. Now moving on to the next clause, D1.3. The maximum moment calculated as in D1.1 applies only to the middle strip, and no redistribution shall be made. Okay, so basically the value, that is this moment which we calculate using this equation, is valid only in the middle strip. Again, we have explained the same thing. We need to design the middle strip using this equation, and we have to perform the same procedure as we have done in the previous program. Now, after this, it is regarding the provision on which how we have to provide the reinforcement. These clauses we will actually discuss in a later stage. So before that, what we have to do is that we have to see different conditions which can occur or which can come into practical cases. So if you see this table, this is the table number 26, in which we have to find out the value of alpha x and alpha y for performing the design of restrained two-way slabs. Okay, restrained two-way slabs. The other one was for again two-way slabs which are simply supported. Okay, now coming over here, if you see, you can see the type of panels and moment considered. Then we have a shorter span coefficient, that is alpha x. Then we have longer span coefficient, that is alpha y. And for alpha x, we have Ly by Lx ratio given here, and correspondingly we have different conditions on type of panels, interior panel, one short at continuous, one long at discontinuous, like that you have different conditions. Let's see what these conditions mean. And regarding alpha y, again for this condition we have different values, but the Ly by Lx ratio doesn't influence that. For all the cases we can take alpha y from this column. Okay, now we have to actually see what do you mean by these continuous edges and the discontinuous edges and all. So for that, let's take a blank slate. So if you take a plan of a framed structure, see, we will be having say a lot of columns like this. Okay, again we will be having new row of columns like this. So let's take 4 rows of column. Okay, so please assume everything to be rectangle square shape. So I am just drawing 4 rows of column and 4 columns of column. Okay, so and let's, as we do in the field, let's name it. So this is A, B, C, D. Then you have here 1, 2, 3, 4. So suppose you want to call or refer this column, what we have to do is that it will be something like A3. Okay, so here we have A, here we have 3. So that will correspond to this column. Suppose you have to call this column or refer this column, what we can do is that it will be B2. So B and we have 2. So likewise you can refer it. Okay. Anyway, now after casting this column, what we will do is that we will be casting the beam connecting these columns. Okay, so basically we will be having beams going like this in all the rows as well as in the perpendicular direction, connecting the columns also. So at all these locations we will be having beams. Similarly, in the perpendicular direction also we will be having, and please do remember this is the plan view, not from the sideway, it's from the top. Okay, so here also we will be having the beams. Here also again we will be having the beams, and you will have beams connecting all the columns like this if required. Again, sometimes we will not be having the beams because there may be some requirement from the aesthetic view of that. Okay, so after this what we will do is that we will have slabs provided by using these beams as the support. So we will be having different segments or different slabs like this. On all these openings we will be having some slabs running like this. Okay, so I am providing different hatching for different rooms. So here also you have some sort of things like this. Okay, so this is the general thing that we usually see in our practical case. So let's take this panel. So panel means it is actually one of the slab that is coming in between these beams. So let me take this panel, that is my panel will be B2, C2, then C3, and finally B3. This will be my panel. Okay, so that means this panel. Right now I am considering this is the panel which I am considering now. So if you see this slab is actually continuous on this edge. So if you see here, you have another slab here present here. So it is as far as we consider this slab, it is continuous to this side as well as this side, as well as this side and this side. So basically this slab is continuous on all its sides, that is it is continuous on all the four sides. So this is what you call by continuity. So basically if you take the cross-sectional view, what you can see is that this will be our slab. Okay, and this will be your column. So it will be actually supported like this, but this slab is actually going continuously to the next panel. So next panel is also continuous Right now we are dealing with this slab. So basically on all the four sides you have continuity. In cross-sectional view you can see two sides. So basically in this side you have continuous slab, and on this side also you have continuous slab. So this is what we mean by continuous. And what do you mean by discontinuous? So let's take an end panel, a corner panel, this panel. Okay, so please focus here on this panel. So if you take up this panel, what we can see is that it is continuous on this side. On this side it is okay, it is continuous, and on this side also it is continuous. It is having a continuous slab. But what about these two sides? This side as well as this side, you don't have any slabs. So basically it is discontinuous at this location. So in such cases we call that at that location it is discontinuous. So if you take the cross section and see, what you can see is that on one side you will be having something like this, and on the other side we have a continuous slab going like this. So this is what you mean by continuous and continuity and discontinuity in the panels. Okay, I hope the concept is clear to you. The main thing that you have to notice that when you have a continuous beam or continuous slab like this, you basically will have a positive moment here on the mid span, and you will face a negative moment at this location, that is at the support location. So basically you will be having a negative moment also, negative and positive moment. So basically the negative moment in the normal case it will be on the support, and the positive moment will be at the mid span. I hope you are able to get the concept. So basically when you have a continuity, you will have two types of moment. One is negative and another one is positive. So basically this positive moment will try to bend the slab in the downward direction, whereas the negative moment will try to bend the slab in the upward direction. So if you see the bend profile, so I am drawing it exaggeratedly. So what will happen is that at the supports you will have a bend in the upward direction, at the mid you will again have a curvature in the downward direction, and again in the second support you will have a bend in the upward direction. So this is what will happen. So but this will not be there if you have a discontinuous edge. Basically at discontinuous edge you will not be having any negative moments. So in such case you will be having only the positive moment at this mid span, but on this end you again have a negative moment. Suppose you have just 4 columns. Okay, and I am providing, just keeping a slab on top of this. If you consider this slab, it is discontinuous on all the 4 sides. That means there won't be any negative moments. Negative moments will not be present in this particular case because it is not at all continuous along any of its edges. So if it is continuous at any of the edges, you will have a negative moment. That is what you have to understand. I hope that thing is clear to you. So based on this, they are actually giving different coefficients for alpha x. Alpha x value will be different based on the type of the panel you are choosing and the span along which you are designing. Okay, so let's take one. So again coming back to this, that the first panel which we consider, that is that panel was actually having continuity on all the sides. Such a panel is normally called as interior panel. It is a interior panel. So for this interior panel we will be having a continuity on all the sides. So basically on both the directions we will be having a negative coefficient or negative bending moment as well as a positive bending moment. So when you calculate mx or using alpha x, you will be having 2 values. One is for positive moment at midspan and another one is for negative moment at the continuous edge. So basically what you have to do is that you have to calculate both these moments using mx equation, and you have to find out how much reinforcement is required to take up this moment. Then you have to provide the proper reinforcement. So suppose we are talking about a slab like this, say again an interior panel. What you have to do is that based on the positive coefficient, positive value, what you have to do is that you have to design the bending moment here. This is your positive bending moment. Then based on the negative alpha x coefficient, what you have to do, you have to again work out the value of mx and design or see how much reinforcement is required to take up that moment and provide that reinforcement here on top of your support. Similarly, using this positive moment, you have to design the reinforcement at the bottom of your slab. So basically this is the thing. Using this negative coefficient, you have to calculate the moment and design the reinforcement on the negative moment occurring side, that is on the supports. or the continuous edge, and you have to use the positive coefficient for calculating the moment at the midspan, and you have to design the reinforcement that should be provided at bottom of your slab. So the basic thing is that in this continuous case, we will be having the tension faced at the midspan. At the midspan, it will be at the bottom, and at the support, it will be at the top. So accordingly, you have to provide your reinforcement. Okay. So the first thing is when you are going to calculate alpha x, you have to understand what type of panel you are going to design. Okay. In the perspective of your examination, you will be directly asked to design any one type of panel. It may be an interior panel, it may be a discontinuous panel. That is, as our second case which we have drawn, it may be a slab which is just kept on 4 columns or two or 4 walls. Okay, in that case, we will have discontinuity on all the edges. For that also, we will be having some coefficients. Say, please refer number 9. That is 4 edges discontinuous. That was the case for us. So basically, we will not be having any sort of negative moments happening there because we don't have any continuous edges. So that is the reason why we don't have any negative coefficients given corresponding to condition number 9. So if you see here, we have only one line of coefficients, and we have a value for alpha y. So based on these conditions, say let's take one more condition. Say 2 long edges discontinuous. 2 long edges discontinuous. In this case, if you see, you don't have any alpha x negative value for alpha x coefficient, but for alpha y, you have a negative coefficient. So let's refer the figure. So basically, this is 2 long edges discontinuous. So where was that figure? Okay, so if you look here, the long edge is your Ly. Okay, and in this particular case, these 2 long edges are discontinuous. We don't have any continuity on this side as well as this side, but we have continuity on the shorter edges, that is these Lx sides. So when you perform the design for reinforcement along x direction, so in the x direction we have right now Ly, that is our larger dimension. We will not be having any. So, sorry, along x direction means it is along Lx direction. So, when you perform the design along Lx direction, what will happen is that we will not be having any continuity on this side as well as this side. So, we will not be having any negative moments. That is the reason why they haven't provided the value of negative alpha x when we have 2 longer edges discontinuous. Similarly, when you were performing the design in the other direction, that is along the Ly direction, you can see that the shorter edges in that case were actually continuous. So basically, when you perform the calculation, that is My, what will happen is that we have continuity on both these sides. So basically, we will be having some negative moments coming on both these supports. So when you perform the design in the y direction or the My value, you will need a negative alpha y quantity on this side as well as this side. So that is the reason why, based on the condition of the continuity and discontinuity, they have provided negative and positive coefficients in this table, in table number 26. So you can, when you get time, you can read each and every condition. So interior panel means it is having continuity on all edges, one short edge continuous. One short edge continuous means all the 3 sides are free, but we have a smaller edge which is continuous, something like a cantilever slab which is having the shorter edge connected to the building, so something like that. One short edge continuous. Then we have one long edge discontinuous. So basically it is on 3 sides it is supported. It is something like your balcony. On 3 sides it is supported, and on one long side it is discontinuous. Okay. Then similarly we have different conditions: 2 adjacent edges discontinuous, 2 short edges discontinuous, 2 long edges discontinuous, 3 edges discontinuous. Likewise, we have 9 different conditions, and the required coefficient for this is also given to you. So in the problem, based on the given problem, you have to think and understand what type of panel it is. Then only you will be able to perform the design. So let's go back to our problem. So if you come back to this problem, you can see that design a reinforced concrete slab for a room of clear dimension. This slab is just superimposed on a wall of width 300 millimeters. That is, on four sides we have a wall, and this slab is simply kept on that. So basically our problem is 4 edges discontinuous. We will not be having any sort of negative moments. So this comes under the 9th condition, that is 4 edges discontinuous. Okay, this is how you have to understand. The slab is superimposed on walls of width 300 mm, and there is nothing mentioned about the continuity on any of the sides. So basically, let's take it as a slab simply resting on wall and all the four sides being discontinuous. Okay. So now from table number 26, you know how to calculate the value of alpha x and alpha y. In this particular case, we have alpha y by alpha x is equal to 1.25. And let's go back to this table, table number 26. 1.25 means it will be coming in between these two values. And going down, we have 4 edges discontinuous. So our value will be in between these two values. That is alpha x will be in between 0.079 and 0.072. Similarly, we have the value of alpha y here. Okay, so you have to interpolate and find the value of alpha x, and we have to directly take the value of alpha y. Okay, so we will be getting it as alpha x as 0.075 and alpha y as 0.056. So once you get the value of alpha x and alpha y, you just substitute it in the equation. We have already calculated the value of factored load, so substitute that value, and please, I am again repeating, this is Lx, and in the case of My also it is Lx. Okay, since you haven't asked why we are again using Lx in the second equation, I am not giving any explanation, since എന്താ പറയാ നമ്മൾ ആവശ്യക്കാർക്ക് മാത്രം പറഞ്ഞു കൊടുത്താൽ പോരെ, ആവശ്യം ഇല്ലെങ്കിൽ പിന്നെ ഞാൻ പറഞ്ഞു തരേണ്ട കാര്യമില്ലല്ലോ. So again, interested ആണെങ്കിൽ നിങ്ങൾക്ക് അന്വേഷിക്കാം. So again here we are repeating it as alpha x itself. That is not a mistake. It is intentionally given as alpha Lx itself in the case of calculation for My. So substitute the value and find the value of My and Mx. Okay, so once you have the moment acting in x direction and y direction, what we have to do? Now the procedure remains the same. What we have adopted for simply supported slabs, we can use here. We have to check whether in the initial step we have made an assumption regarding the overall depth. Now we have to check it in perspective of the strength criteria or the over reinforced criteria, and as well as we have to prove that it is safe in as far as the condition for deflection is considered. So and again, for examination, some of you have just performed the design up to this point. That is, they have just used this equation and calculated the minimum depth required, and once it was safe, they have just concluded that the design is safe, and they haven't even calculated the AST. I don't know what they mean by design. Okay, so basically here what we do is that we will use this equation corresponding to balance section, and we will calculate the minimum depth required for ensuring that our section will not be an over reinforced section. So this is the minimum depth required for a balanced section. So we have already assumed a very higher value, almost double the required value. So it is perfectly safe, and it is again an under reinforced section. So we can use the equation corresponding to under reinforced section for the calculation of our AST. And again, please note, at this particular stage, we are designing for the middle strip alone. So the width of the middle strip will be, as we have already seen, it will be 3/4 of your Ly. So basically, as per the figure given in your IS code, you can see that when you perform or calculate the reinforcement along the x direction, they have actually kept this figure like this. That is the reason why we are also following the same. So we are just now designing in this direction. So first thing is that we have to find out the width of this middle strip, that will be 3/4 Ly. So coming back here, 3/4 Ly, that is equal to 3.9 meters. Now what we have to do, for this much width, what is the bending moment acting and what is the amount of reinforcement that we have to provide? That is what we are going to calculate now. So using the equation corresponding to an under reinforced section, substitute the values and find the value of your AST from this basic equation. This thing we have already done many times, so I am not spending much more time on this. So once this is done, we have already assumed that we will be using 8 mm diameter bars when we assume the value of effective depth. So based on the same diameter bars, we will be calculating the spacing requirement. So spacing is equal to 1000 into area of one single bar divided by total AST, which is required. Okay, so substitute that and find a spacing and round it off. In this case, it is coming around 151. So they have just rounded it to 150 mm. Okay, and again, as per your clause given in IS 456 regarding the maximum and minimum spacing, you have to ensure that this is satisfactory. Okay, we are proposing to provide it a spacing of 150, but if the minimum spacing as per the condition given in the code is less than this, we have to stick on to that. Okay. Now this is safe as per the clauses. So I am again providing the same value. So the actually provided value is 1000 into area of single bar divided by the spacing. That is 335 millimeter square. Now what I have to do? So before this, we have one more step. So that is not shown here. After this, what we have to do is that based on the amount of reinforcement provided and the amount of reinforcement required, we have to calculate the value of Fs. And with respect to figure 4, which we have already done in the previous problem, we have to find out the modification factor, and we have to ensure that the condition for deflection is satisfactory. Okay, that is satisfying. The depth is enough to ensure that the deflection will be within the limits. So those procedure we have already done in the previous problem. That is why that may be the reason why they haven't repeated it here. So please understand that at this particular step, after providing the spacing, you just recalculate the total amount of steel provided. Then you just ensure or show that as per the condition of control of deflection also this will be satisfactory. Or during the examination, what you can do is that another thing to save some more time is that during the initial phase you should not make a direct assumption. Instead of that, based on the span to depth ratio given in the clause, in the initial clause, so that was for simply supported, it was something 20, and likewise you have different ratios, right? You just stick to that, so that you need not again worry about the total amount of steel provided and the actual requirement, and you have to again calculate Fs and finally prove it. So those steps can be avoided if you are sticking on to the initial ratio. But as per economy point of view, it is not a correct manner. So you have to actually perform or take up a smaller dimension, and practically if you are just sticking on to the same value given in your code and you are saying that you need some 25 centimeter depth slabs and all, ഫീൽഡിലുള്ള ആൾക്കാർ നിങ്ങളെ കളിയാക്കുള്ളൂ, അത്രയൊന്നും ഒരിക്കലും നമ്മൾ കൊടുക്കില്ല. So basically you must also have an understanding about the dimension that we provide in the field, and you have to understand the concept. So for your examination, in order to save time, if you want, you can just directly stick on to the ratio given in your code and go with that, so that you can avoid a lot of steps. So that is another thing. So no one can tell you that the procedure is wrong, but in economic perspective of view, it is wrong. That's it. So once we complete the or find out the amount of reinforcement required along the x direction, we have to also perform the design and find the reinforcement requirement along the y direction. And as per the figure given in your IS 46, LX is actually spanning in the y direction. So they have taken calculation of steel reinforcement in the y direction, and they are talking it in terms of LX. So the width of middle strip is calculated as 3/4 of LX. Again, we have the effective depth recalculated, because on one side we have already provided the main reinforcement. When you look from the second side, you will be having the main reinforcement, and the actual reinforcement in the second side will be provided on top of that. This thing we have discussed in the previous problem. So your effective depth will be slightly different actually if you are completely sticking onto the theory. Okay, so you just recalculate the effective depth in the y direction, and you again calculate the moment, means AST, based on the under reinforced equation itself. So we have already proved that the provided depth is larger, means provided depth is larger than that of a balanced section. So it is anyway under reinforced section. So on both sides the depth will be same, right? So you just calculate the AST and provide the required spacing. And after this, what you have to do is that you have to perform the design for the edge strip also. So for edge strip, what we will do is that in the code itself, it is mentioned like, where is that clause? Let's see here on D1.7, reinforcement in the edge strip parallel to that edge shall comply with the minimum given in section 3. In section 3, we have the condition for the requirement of reinforcements there. The minimum regarding that is 0.12%. So basically we are sticking on to 0.12% of the cross section. So we will calculate the AS minimum as 0.12%, and that is, in this case, it is coming around 216. So assume some diameter of for the bar and find the spacing, and also check the maximum allowed spacing, and finally provide that in the edge strip. Okay, and they are just calculating the width of edge strip here, and they will be providing the reinforcement in that edge strip. So after this, anyway, it's time today. So after this, we have the check for shear, and we have to actually provide some torsional reinforcements also that we will see in the next class. Anyway, this will be the configuration of reinforcement. We will be having some reinforcement in the middle strip, and we will be having some other reinforcement in the edge strips. So this will be something after providing the torsional reinforcement also. Some sort of, say here it is clear, very clear. It is at the bottom part, we will be having some sort of reinforcement spanning in both this direction, only in the middle strip. If you see that in the edge strips, we have a lesser number of reinforcement. So basically we are just providing the AS minimum there, 0.12% of the cross section. That is the reason why we have a larger spacing at the edge strips on both sides. So we will look into this thing in detail in the next class. Anyway, for this, we are stopping it here. Okay, so this was the problem which we were discussing. So basically, we were having a slab, a room of internal dimension 4 meter by 5 meter, and we are supposed to design a slab for that. And it is mentioned that the slab is superimposed on walls having width. So basically, the width of support is given to you, and the same is 300 millimeters. The slab is again told to carry a live load of 4 kilonewton per meter square and a floor finish of 1 kilonewton per meter square. And we are supposed to use M20 grade concrete and Fe415 grade steel. This was our question. Slabs are held down, that is, it is a restrained slab, and again, since this slab is superimposed on walls on all the sides, it can be considered as a discontinuous slab. So on all 4 sides it is discontinuous. So these are the things that you should note from the statements given in the question. So once that is done, we are calculating Ly by Lx ratio so that we can classify it as 1-way or 2-way slab, and that we have already done. We have found out the effective depth, assuming an overall depth of 180 millimeters. Then based on this effective depth, we have calculated the effective span in x direction as well as y direction. That is Lx and Ly, and it was obtained as 4.161 meters along x direction and 5.161 along our y direction. Now, in the next stage, we have calculated different loads. So basically, since we have finalized the depth of our slab, we can calculate the dead load. Then we are provided with the value of finishes. So the total dead load will be the sum of sulfate of slab as well as this finishes. Then we have one more thing, that is live load. So the total factored load will be factor of safety multiplied by sum of dead load and live load, which was coming around 14.25 kilonewton per meter square in this problem. Then what we can do is that we have to calculate the value of mx and my. So for this, since we have a restrained slab, please do note it. When we have a restrained slab, we have to refer table number 26. If we were having a simply supported slab, as we have done in the previous problem, we have to take alpha x and alpha y from table number 27. Okay. So this is the case of restrained slab. So accordingly, we have taken. So based on the type of panel, that means whether the slab is continuous on all sides or whether it is continuous on one side and discontinuous on another side. Likewise, different conditions are given there. So based on those conditions and Ly by Lx ratio, we have selected alpha x and alpha y, and we have substituted these things and calculated the value of mx and my. And the values obtained are mx is 18.50 and my was 13.81 kilonewton meters. After this, what we have done is, as the normal procedure, we will be checking for the minimum depth requirement based on the equation corresponding to balance section. So in this case, the minimum depth requirement in this regard was 82 millimeters, which was very much lesser than the value of depth we have already assumed, that is 161. So it is safe. Also, the section is under reinforced because we have a larger depth in comparison to the depth of depth of our balance section. Okay. Now what we have to do is that we have seen that in the case of restrained slab, we have to actually split the slab into 3 parts along x direction and y direction, which constitutes 1 middle strip and 2 end strips on both the directions. So basically in the x direction, we are now going to calculate the width of middle strip. So again, it is given in the code that the width of middle strip should be 3/4 of the total length. Okay, whether it be in the x direction or whether it be in the y direction, it will be middle strip will constitute around 75% of the total length, and the remaining thing will be equally distributed on both the edges as edge strip, which can be calculated as 1/8 of total length. Okay, so you will be having 1/8 length on left side as well as 1/8 length on right side, and in the middle you have your middle strip, which will constitute the 75% or 3/4 of your total span. So based on this, we have calculated the width of middle strip, and in this case, when we consider the direction of Lx, it is coming around 3.12 meters. So in the next stage, what we have done is we have just found out the AST requirement based on the equation corresponding to under reinforced section. So basically here you have to substitute the value of mx, that is 18.5 into 10⁻⁶. Please do note, when we are designing along the shorter span, that is Lx span, we have to substitute the value of mx, and when we are designing along the larger span, that is Ly direction, we have to substitute it as my and calculate the AST requirement in the respective directions. Okay, so in this case, this AST is coming around 332.5 millimeter squares, and we have already assumed that we will be using 8 millimeter diameter bars. So the spacing requirement based on this can be calculated, and in this case they have found it as 151 millimeters, and they have provided 8 millimeter bars at 150 millimeter center to center. Okay, and again here you have to actually perform the check for maximum and minimum spacing. So in the examination also, last examination also, many of you haven't done that check. That is one of the important thing. Otherwise, for your university examination, you will be losing 1 or 2 marks. So based on the diameter of the bar and the obtained spacing, we are providing 8 millimeter diameter bars at 150 millimeter center to center along the shorter span. Okay. Now the provided area will be coming around 335 millimeter square, and if you since we have made an assumptions regarding the overall depth in the initial stage, we can refer figure 4 and show that this case is satisfactory under the control of deflection criteria. Okay, I am not repeating that procedure here. Now what we have to do is that we have to find the AST requirement in the other direction, that is in the direction of Ly also. In a similar fashion, only thing is that the depth will be, the effective depth will be slightly different, and again this thing also we have already seen. So we will be providing the main reinforcement in the perpendicular direction above the main reinforcement, which we have already designed when considering the shorter span. So we have seen that there will be a difference in the diameter, so consider that and find the revised diameter. Then based on again from the same equation and substituting the value of my instead of mu, you find the value of AST requirement and provide some find out the spacing and provide reinforcement. In this case, they have provided 8 millimeter diameter bars at 190 millimeter center to center, and the actual area produced is 264.74 millimeters. So basically this design is actually for which part? It is for the middle strip along the shorter direction as well as in the longer direction. Please do note that this procedure is, by this procedure we are actually finding out the AST requirement for the middle strip alone. Okay, so this doesn't complete the entire design of your two-way slab. Right now what we have done is we have just designed the reinforcement requirement in the middle strip along the shorter direction as well as along the longer direction. Okay, now we have the edge strips. In both the directions we have the edge strips. So the area of steel requirement in both these strips are minimum requirement. As per the code, we have seen that in Annex D itself, a clause is given that you can stick on to the minimum requirement as provided in the respective clauses, and we can see that if you refer that clause, you can see that it is 0.12%. So basically you have to calculate 0.12% of the total cross-sectional area, not the effective depth, it is the overall depth. Okay, total cross-sectional area of this thing, and it will come around 216 millimeter squares. So you assume some sort of diameter. It is always preferable to adopt the same diameter. In practical point of view, it is always preferable to adopt the same diameter as you are using for the middle strip. So it will be easy when procuring things. So diameter of bar, again here they have selected it as 8 millimeter itself. So we can again calculate the spacing requirement, and the maximum spacing requirement should be checked so that it ensure that it is not exceeded. It is 5D or 450 millimeters in the case of secondary reinforcement. Okay, so you use this condition and provide the reinforcement in the edge strip also. And another thing is that now we have to mark the edge strip as well as middle strip so that we can provide the designed amount of reinforcement in the respective parts. Okay, so what we can do is that we have to provide 8 millimeter diameter bars at 230 millimeter center to center in the edge strip of width half into This is along the other direction. 5.16 is the Ly value minus 3.9. 3.9 is the width of middle strip. That will come around 1.04. Okay, is that correct? Okay, we will just give me a minute. I think there is a mistake in that. 19. So there is slight mistake in that calculation. It will be coming around something 0.640 or something. So you just work it out. Anyway, I have already told that there can be numerical mistakes in these things. So you just find out the width of edge strip. How to find that? Say suppose you are considering the shorter span, that is Lx span. What we can do is that it will be equal to Lx divided by 8. That will be the width of your edge strip. And again, if you forget this, you can refer Annex D. There they have given the picture showing the edge strip and middle strip, and the respective values are also shown in that picture. So in case you forget, you can refer your code and again understand this. Okay, so based on that, you provide edge width as edge strip width as the total span, whether it is the Lx or Ly, that divided by 8, and middle strip will be 3/4 of Lx or Ly in both the directions. So you just calculate that. After that, we can provide the reinforcements. So again, the design for shear is same as what we have done in the normal slabs. So you perform the design for shear also, and in this case also there won't be any need for providing stirrups. Normally, also please understand that now in the normal case we will not provide shear reinforcement in the case of slab. If such a condition arises, see based on the condition that tau v is less than tau c by 2, only we are avoiding shear reinforcements. If in your design such a condition arises, what you can do is that you can increase the depth of slab and redo the calculation. Normally, it is not preferred to provide any sort of shear reinforcement in the case of slabs, and it is not a practice to provide shear reinforcement in the case of slabs also. So please keep that in mind. Okay. So that is regarding the normal design. Now, before moving on to the torsional reinforcement required, because the edges are actually restrained from rotation, so there will be some torsion produced in that, and we have to provide some reinforcement to ensure that it will not fail in torsion also. So we will see to that. Before that, let us check out the reinforcement which are provided. So basically, this is along the Lx direction. So you might have calculated the, and again, here you have some mistakes. So please understand. What you have to do is that you have to provide reinforcement in this direction. This line represents the reinforcement which you have designed based on the Lx value, shorter span. For shorter span, if you go back and see, where is it? So this one. So when you designed based on Lx, so this is the Lx value, and we have substituted Mx here and found out the AST. It was 8 millimeter diameter balls at 150 millimeter C by C, center to center. So this is actually provided here. This is your shorter span, and if you see, you can see that 8 millimeter. This hash represents HYSD bar. Okay, this hash actually represents HYSD bar. 8 millimeter diameter at 150 millimeter center to center, and you can see that this line is actually representing this one, 8 millimeter at 150 millimeter C by C. And again, if you see here, some of the bars are actually bent up, and even though we have a discontinuous edge here, some of the bars are bent up. So let's see how much bars should be bent up and at what spacing. And there they have given it as 8 millimeter phi at 300 millimeter C by C. That is double this spacing. This is 150. This is 300 millimeter C by C. Let's refer the code for this. So if you come back to the code, here we have a clause like this. So at a discontinuous edge, negative moment may arise. It may arise due to some restriction on the rotation. So they depend on the degree of fixity at edges of the slab. I don't know whether I have shared with you. You might have learned that we have some sort of fixed support, we have some sort of hinge support, and different supports we have already learned. But please do understand that in actual practical case, we don't have any specific fixed support or hinge support. Things will be in between these. We cannot tell that it is completely fixed or completely free to rotate. Okay, such conditions are there, not in the actual practical field, but for the analysis, we will assume that it is perfectly fixed or perfectly hinged. But in the actual case, it may be in between this one. Okay, so please keep that in mind. So at a discontinuous edge, negative moments may arise. They depend on the degree of fixity at the edge of this slab. But in general, tension reinforcement equal to 50% of that provided at middle span extending 0.1 L, that is Lx or Ly, into the span will be sufficient. Okay, so basically what we have to do here, so even there can be, they are telling that even the end is discontinuous, there can be chances for negative moments to be developed. So for taking up that, what we have to do is that we have already designed 8 mm bars at 150 millimeters center to center in the middle strip. So these bars, the 50% of these bars should be bent up like this. It should be bent up and provided like this. So 50% of these bars means, say we have provided at a spacing of 150. So if we are increasing or doubling the spacing, that means we will be providing half of the area of the reinforcement which we were having. Are you getting that concept? Right now we have provided 8 millimeter bar at 150 millimeter center to center. If we are doubling the spacing means each and every alternate bars will be taken up. See, I think this figure will give a more clarity on that. Say suppose this spacing is 150. Say the provided spacing here is 150. I am increasing this spacing to 300 means what I will do? I will keep this bar, I will take out this bar. This bar will not be there. So this 150 means 300. Now I will keep this bar and I will take out this bar. Therefore again I have a 300 spacing. So in effect what we are doing is that we are just providing or making half or providing half the actual AST. So for that what we will do is that half of the bars provided at the middle span will be bent up like this. Mainly what we do is that we will be bending alternate bars. That means the spacing will be doubled. That is the, and again this value is not the correct one. We have to actually provide 8 mm bars at 300 millimeter spacing. So please note again we have a correction here, 8 mm bars at 300 millimeter spacing. Again this is based on this condition that we will be in need of providing, say at a discontinuous edge, negative moments may arise. They depend on the degree of fixity, and in general, tension reinforcement equal to 50% that provided at the midspan extending to a length of 0.1 L into the span will be sufficient. Okay, that much should be provided to take up the negative moments that may arise. So that is what court is suggesting. That is the reason why we will be providing at a double spacing at the support. Okay, so that is one thing. Now moving on to the second figure. Sorry, it's 150. So sorry, it was actually correct. I was referring the wrong figure. So if you see this, this was our shorter span. So here you have 8 mm at 150 millimeter C by C, and please see this. It is 8 mm at 300 millimeter C by C. That is what is provided on top. That means 50% of the reinforcement we have in the middle strip is bent up and provided there. Then, and again they have marked the edge strips and middle strips. So in this figure, if you see, this is the plan of bottom reinforcement. So basically what we have done is that this part constitute your middle strip. Okay, this part constitute your middle strip, and if you are referring the longer direction, we have a edge strip here, we have a middle strip here, then we have another, say I think it is better to mark it there. So in this, basically we have a edge strip here, then we have a middle strip here, again we have a edge strip here. Similarly on the other direction also we have one edge strip here, and then we have one middle strip provided here, and we have further one edge strip. Okay, so we have designed the reinforcement for these middle strips as well as edge strips. So at the bottom side, we will be basically having, say, let's take the larger direction, this direction, LY direction. In this, first thing that we have done is you have designed, say if you take the cross-sectional view, it will be, I am roughly drawing this. So basically when you consider this direction and design the reinforcement, you will be providing the respective reinforcement like this, isn't it? So these things, this one, again this one, these all will constitute the reinforcement which we have designed now. Okay, so and again if you refer that, so somewhere say here if you refer these reinforcement, this one and this one are actually shown by this arrow, and it is 8 millimeter at 190 center to center spacing. That is the reinforcement we have already designed with respect to Ly direction. So if you come back to the design, when we designed with respect to Ly direction by substituting the value of My, we obtained an AST, and we have finally provided 8 millimeter diameter bars at 190 mm C by C. That is what is shown in this diagram. Okay. So that is what is shown here, 8 millimeter at 190 mm center to center. And when we designed with respect to this LX direction, we obtained it as 8 millimeter at 150 mm. So that is what is they have shown here. This one, and this one. Okay, so what happened at the edge strip? So let's take the case of Ly direction. So we have eight number of bars at 190 mm center to center spacing in the middle strip. But if you observe here, you can see that this first reinforcement, this is actually spanning through the edge strip at the bottom part. Okay, this one is your first reinforcement. This is actually spanning up to this point. After this, what they have done is the next one is not visible after this point. At this particular point, please note, we are looking from the top, and again we are focusing on the reinforcement at the tension side, bottom part. So here what they have done is they have just bent it up, and this reinforcement is actually spanning on the top of this slab. That is why we are not able to see that here. But if you refer the next figure, you can see that reinforcement is here. This top portion only. The other things cannot be visible in this because this is plan of top reinforcement, not the bottom reinforcement. Okay. Now we have went up one bar. After this, the next bar is directly extended into the edge strip. Then we have again for the next bar, we have bent it at this location. Then alternate bars are completely extended and the alternate bars are bent up. So we have 50% of the total AST on the top side at the edge also. So this is how we have to actually provide it. So basically, since we are increasing the spacing at this edge strip, what will happen is that this spacing will be the double of that of what we have provided in the middle strip. In this case, in the Ly direction, the spacing which we have provided at the bottom was 8 mm at 190 center to center. So at the edge strip on top side, we will have 8 mm at 380 mm C by C. So this is how we have to provide the reinforcement in Ly direction, as well as in a similar fashion we have to provide in the Lx direction also. This will feel a little bit complicated now, but you please take your time and observe this figure and compare with the values which you have obtained for your design, so that things will be clear to you. This is actually a very simple thing. Since they have given all the reinforcements simultaneously, that is what is causing this confusion. Okay. So that is one thing. That is the reinforcement, how to provide the reinforcement we designed based on design for middle strip. Now we have one more thing. That is our edge strips. That is 0.12% of that thing. So if you are again talking in terms of Ly, these were actually reinforcement we have designed for middle strips. And if you observe, we have a edge strip here also. No, not here. Here also we have a edge strip. This was our middle strip. This is middle, and this is our edge strip. Okay. So here we have designed for 0.12%. So that also should be provided here. If you see that we have reinforcement provided like this way also in the edge strips. Okay. So that reinforcement also should be provided in this. So that should be also provided along with the reinforcement that you have provided in the middle strip. Okay, in a similar fashion, we will be having edge strips in the other direction also. So the reinforcement which we had designed should be provided there also. So if you come back here, I think in both the directions we are providing 0.12% of the cross section, so this thing will be same. So we are basically providing 8 millimeter diameter bars at 230 mm C by C in all the edge strips. Okay, so that also should be marked in your final detailing diagram. Now, once this is done, one more thing which is remaining is the design for torsion. Okay, so before moving on to that, let's go back to our code. And in D1.8, they have clearly mentioned that. So because since we have a restrained slab only, we need to go with torsion. So torsional reinforcement shall be provided at any corner where the slab is simply supported on both edges meeting at that corner. Okay, so the conditions are like this. Both on that corner, the slab should be simply supported. The torsional reinforcement shall be provided at any corner where the slab is simply supported on both the edges meeting at that corner. Okay, it shall consist of top and bottom reinforcement, each with layers of bars placed parallel to the sides of the slabs and extending from the edge a minimum distance of, you please note down this, 1/5 of the shorter span. So basically the minimum distance through which we have to provide torsional reinforcement is 1/5 of the shorter span. The area of reinforcement in each of these layers, 4 layers, shall be 3/4 of the area of reinforcement for the maximum middle span moment. That may be mx, that may be my. You have to select the larger value and you have to find 3/4 of that area, and you have to provide reinforcement corresponding to that which value, 3/4 of largest of mx and my, and that too through a distance of 1/5 of the shorter span. So whatever things you need to notice, 1/5 of the shorter span is the distance through which we have to provide the reinforcement. Area of reinforcement should be corresponding to the 3/4 of the maximum value of mx and my. I will just in simple words I will tell you how to provide this reinforcement. So basically mesh size. So basically what we have to do is that, so we will be providing this reinforcement as mesh. So if you see this figure, you can see that you have many number of reinforcement going in both this direction. This forms a mesh, and this will be provided at the bottom as well as at the top. So basically if you are taking a cross-sectional view, say if you are taking the cross-sectional view, I am just drawing the mesh alone. So on top part we will be having a mesh. Similarly on bottom also we will be having a mesh with the same. And this dimension, this 840, corresponding to what? It is the, how we can find that value? The length through which this reinforcement must be extended is shorter distance by 5. That is what is mentioned in the code. So you just calculated the value corresponding to shorter distance, that is Lx by 5. In this case it is coming as 840. So basically this mesh will be a square mesh, and this mesh will be, it will be like this. This will be the mesh. Will be having many reinforcement. How to find the spacing of this reinforcement? That I will explain. So this is Lx by 5, and this side also Lx by 5. Okay, and now how to find the diameter and the spacing? So basically what you have to do is that you have to first of all take mx, my. You take the larger one of this one. Let's assume that mx is larger. In this particular case, mx is larger. Then what you have to do? You have to find 3/4 of mx. And then you have to assume a diameter of what? Say, let's take 8 mm, 5 bars. Then you just find out, say, this will give you an AST for your this torsion. You assume a diameter for your bar. Then you find out at how much spacing we have to provide this 8 mm 5 bars, so that we will be getting this AST as we usually calculate in the case of slabs, and provide this mesh. So basically this spacing will be the spacing that you obtain from that. So that is what we are doing here. So area of torsional reinforcement is equal to 3/4 of the largest of mx or my, and that is coming around 251 millimeter square. Again, we are providing 8 mm diameter bar. So the spacing required is 201 millimeters. So provide 8 mm mesh of bar at 200 millimeter C by C. So basically we will be having only 4 number of bars in both the direction, not as what we see in that figure. So the total is 840. 4 or 5 maximum to the maximum. 1, so 200, 400, 600, 800, and maybe we will be having some more spacing there. So in the similar fashion, we will be having few values. The mesh will be only this much. So this is how you have to provide the mesh. Only thing is that we have to provide the mesh. If you take the cross section, we have to provide the mesh on top as well as on the bottom. So that is the reason why when we take a plan of bottom as well as top, we are observing a mesh. Say this is the plan of bottom reinforcement. We have a mesh on 4 corners because all these 2 corners, and the condition is when you consider this corner, this side should be simply supported, this side also should be simply supported. If we have provided at the bottom a mesh like this, and if you refer the plan of top also at the very same location, we are again able to see this mesh, because this mesh is actually provided on top and the previous one was actually provided at the bottom of the slab. Okay, so after completing up to this point and drawing this detailing, your design problem for restrained slab will be over. So this is how you have to perform the design for restrained slabs. So the main difference, if I am telling you, we have to split the slab into middle strip and edge strips, and edge strips will constitute 1/8 of the respective span, and middle strip will constitute 3/4 of the respective span, and you have to perform the design for middle strip. You have to calculate the actual AST for middle strip and provide minimum amount of 0.12% of the cross section reinforcement corresponding to 0.12% at the edge strips. Then in addition to that, you have to check each and every corner, and if both the edges meeting at that corner is simply supported, you have to provide torsional reinforcement, which should be provided for a width equal to what? 1/5 of the shorter dimension, that is your LX, and the spacing of the bar should be calculated based on 3/4 of largest of MX and MY. AST required for carrying 3/4 of largest of MX or MY. Okay, so this is how your final detailing will look like. We will be in need of providing a planet top and planet bottom. So we have bend bars at all the edge strips. So we will be having some middle strips here, and it will be bent at this location. Similarly, on the other direction also, we have bars spanning in this direction, and this should be bent up, because it is in the code. It is clearly mentioned that 50% of the reinforcement should be bent up. Even we have a discontinuous edge, 50% should be bent up. Okay, so I will just add few more points which are discussed in your code. So if you come back here, in the restraint slab, we have seen these clauses. These are defining how to calculate the value of MX and MY. Then below that, slabs are considered as this thing also we have explained. This one also we have seen. Now D1.4, let's see what we are having there. Tension reinforcement provided at middle span in the middle strip shall extend in the lower part of the slab to within 0.25 L of a continuous edge. So basically what we mean is, so we will be having some reinforcement we design in the middle strip, and this should be actually extended to the edge strips also, or edge strips through a length equal to 0.25 times Lx or Ly, depending on the direction which we are designing, for a continuous edge. If we have a continuous edge, say suppose I am considering this slab and I am talking with respect to Ly direction, and on both these directions I have a continuity. This side is continuous and this side is continuous. In that case, I have to extend the reinforcement which I design in the middle strip through a length. On this side, I should extend it to a length of 0.25 L, or else, suppose this was not continuous, it was actually discontinuous, as in the case of our problem, we have to extend that through a distance of 0.15 times Ly in this case. Okay, 0.15 times Lx, I should extend that. So that is another condition that code suggests you. Then we have few more conditions. Over the continuous edge of a middle strip, the tension reinforcement shall extend in the upper part of the slab of 0.15 L from the support, and at least 50% shall extend to a distance of 0.3 L. So basically, when we have a continuous edge, right now we have taken up a problem which we have discontinuous edge on all the sides. So there can be cases where we have continuous edges. So in that case, what we have to do is that this tension reinforcement should be bent and projected in the upper part of the slab also when we have continuity. Okay, in the upper part of the slab through a distance of 0.15 L, and this after bending it up, it should extend through a length of 0.15 times. Say if you are speaking from this side, Ly, 0.15 times Ly, that too from the support. So suppose I have the support here, I have to extend beyond that through a distance of 0.15 times L. So to make things more clear, so basically this will be the case. So we have a continuous slab like this. This end is continuous. Okay. So basically we have designed some thing like this, and this should be bent up. And here also it is continuous, so it will be having the same case. So basically what they mean is this distance should be what was that dimension? It was 0.15 times Lx. It should be this part. Okay. This part should be 0.15 times Ly or Lx. Similarly, on with respect to this second slab also, you have to provide this distance as the respective 0.15 times the span here on this direction. Okay, so that is what is suggested by the code in this case. So any more things? This we have already discussed. Reinforcement in the edge strips parallel to that edge shall comply with the. This also we have discussed. That is how we arrived at 0.12%. Then regarding torsional reinforcement, then we have torsional reinforcement equal to half that described in shall be provided corner containing edge over only one of which slab is continuous. Again, please note this D1.8 was a case where when we consider the corner, say for example in this case, when we consider this corner, both these edges are discontinuous. So this was the case with respect to D1.8. But there can be another case where we may be having a discontinuous edge and this side may be continuous. So in that case, what we have to do? In that case, the torsional reinforcement equal to half that described here. So we have calculated 3/4 of maximum of mx or my and calculated the AST corresponding to that. We have to provide only half that AST. So torsional reinforcement equal to half that described in D1.8 shall be provided at a corner contained by edges over only one of which slab is continuous. Other will be discontinuous. So that is what is defined in 1.9, and moving on to 1.10, torsional reinforcement need not be provided at any corner contained by edges over both of which slab is continuous. And if both the sides are continuous, we need not provide any sort of torsional reinforcement. So again, Ly by Lx is greater than 2 means it is again one-way slab. So we can design it as a one-way slab. So these are the details given in your Annex D regarding the design of two-way slabs.